since we're 4 minutes in. So today I'm going to talk about the Josephus problem and the solitaire encryption problem. Okay. Now, once again, either of these are, you choose one of them, and you do you choose one of them. You don't do both of them. The solitaire encryption takes much longer, but it's worth 20 extra points. So it's also called the PDF is called Pontifex because as you'll see from the book it came from, it was called the Pontifex cipher. But I'm going to go and talk about both of these. Okay. So first, but before I do that, I'm going to download the circular linked list code, and I'm going to just simply quickly glance at it with you. I use VS Code a lot of time when I'm just going to. So I have it in a package. You can remove that package declaration if you want. That's no problem. That just simply means it expects to be inside your SRC folder. It expects to be inside a circular linked list folder. You can, if you don't want that, no worries. You can remove that. It's no problem whatsoever. Okay. A circular linked list implements iterable, so that's so that it can have an iterator. In other words, you could technically use a for each loop on this thing. Don't, because it's never gonna stop iterating through it because of the way it works. And head, tail, size. Circular linked list. You'll need to implement get node, add. This really only has one change that needs to be made to it, which is that false statement, and then remove. Okay. The two string, so those are what you need to implement to get the circular linked list working. Circular linked list is just like a regular linked list, except the head, the tail of the linked list always points to the head of the linked list. Otherwise, you can follow the doubly linked list videos, and there'll be a great guide for how you can code this up. Now, it's a singly linked list, the doubly linked list. Even though this is a singly linked circular linked list, you'll want to follow the directions because they have the same cases, because we keep track of the tail. Okay, the toString, I wrote the toString so that you can print it out, so you can just simply make your circular linked list and print it out. If it crashes, that's on purpose for the toString. The toString is designed to crash if your circular linked list is not working. Okay. We also have this iterator, which is useful if you're doing the Josephus problem. Part of doing the Josephus problem is looking through the iterator and reading through my comments on how to use it. And you can use the iterator to manually iterate through, so you don't have to worry about the indexes, keeping track of what indexes are. And I'll explain why that's something in a second. And same, here's the node. Don't change it unless you want to make it harder for yourself. All right, so Josephus problem. So the Josephus problem is named after a historian, Titus Flavius Josephus. So Flavius Josephus. Now he was this historian, a very early historian, not one of the earliest, but I mean, like, he was note the time he lived, AD 37 to 100. He was a Roman Jewish historian, and he wrote something called The Jewish War, but he wrote a bunch of other things. Anyway, world history during that time, the Roman Empire was the dominant power in Europe and basically had, territory everywhere in, over the, across the Mediterranean. Anything the Mediterranean touched, essentially, they could wrest control of. However, because of, the issues with technology at the time and, the fact that that you're doing empire building, you get rebellions. You get rebellions everywhere in the time of the Romans. And one of those was the Jewish uprising against the Romans. Now, it went exactly the way all the uprisings against Rome went, which was extremely poorly. So they eventually sent in their legions, and during the siege of and Josephus was a priest and basically a war leader at the time. So he he and his band of remaining soldiers, about 40 of them, they got sieged and surrounded, and the Romans basically offered them the chance, okay, we can come in and kill you all, or you can surrender, and they're like, we can kill you all and just starve you out and let you wait, or you could surrender and become slaves, the idea was, the Jews there decided, hey, we would rather die free men than live as Roman slaves. And so what they did, rather than commit suicide, is that they drew lots. They basically had a lottery, and each time there would be a loser, they would kill the loser. And they did this until only 2 of them remained, Josephus and one other person. And I guess they kind of just looked at each other and went, well, this was a terrible idea, and they surrendered to the Romans and became slaves. Now, Josephus had the amazing prediction that the general who was good at generaling, who became his slave master, would eventually become emperor because he was so good at generaling. But that was divine revelation. And eventually he got he gained his freedom and became a member of the family. He assumed the emperor's family name of Flavius, hence Josephus, Flavius Josephus. So he fully defected to Roman, and he started writing about stuff. So he wrote The Jewish Wars, The Antiquity of the Jews, and so he's primarily noted for 2 things in terms of history. The first is the Josephus problem, which we'll be going over, which has to do with that whole lottery system we were talking about. And the second thing was the fact that he writes about early, Judaism during that time, but also early Christianity. In other words, early Christian Jews, before basically Christianity and Judaism became truly distinct religions from each other. So he provides extra biblical accounts of a lot of figures from the Christian Bible, which is useful for historians of religion because, a lot of the people who appear in the Bible are real people, but, that gets mixed up with religion and stuff. Or mixed in, I should say. So having it's always great when historians can say, okay, this figure or these things involved in history, we have documents at the time, it's great. Now, so those are influenced early Christianity, Josephus problem. So anyway, what the heck is the Josephus problem? So talking about that lots, the traditional idea of it is that they kind of lined up in a circle, and they would count off every other person, and then they would kill and every other person would die until only one person remained. Well, 2 in the case of the story. So over here, this is we basically say that you have a ring of n people, and the kth person is removed. In this case, we have n is equal to 41, k is equal to 3. So in this example, gotta love Wikipedia for their wonderful examples. So 1, 2, remove the third. 4, 5, remove the third. 7, 8, remove the third. And it keeps going around. And then notice once we get back over here to 30, we remove 39, which is a multiple of 3. We go 40, 41, and then 1, right? The person, it wraps around. It does this, it does the whole modular arithmetic thing. But then we do 2, 4. We're skipping over 3 now because 3 got removed, right? And the reason we keep these labels and don't adjust the index is because we want to remember, because the Josephus problem asks, what is the starting position that you want to start at in order to not die? So winning the Josephus problem is basically, just standing in the right place. So over here, it gives these last positions of 16 and 31 because there's, 16 and 31 are last. So there you go. Now, there's a few different variants and stuff like that, and there's a mathematical and this, I'll probably cover this in my next in 3223 when I talk about dynamic programming, because this is a problem that has a recurrence, but and this is the generalized form. Given n people in a ring of k, here's the solution to the problem. Right? It's a lot of math there. A lot of floor notation, modular arithmetic going on there. Bit of a mess. But fortunately, a lot of the times in computer science, we have our options. We could implement this, but we're not gonna. We could implement that math, but that's not really pertinent to the lesson. Instead, the idea here is that we can perfectly represent this as a linked list. So the idea here is that with a circular linked list, we can go around and keep removing and keep iterating through it, removing every kth person until there's only one node left, and we can print it out. So your output, using the iterator, we use .next to advance to go to the next person, and then .remove to remove the person we currently went on. So if I wanted to remove every second person, I would repeatedly do .next, .dex, .remove. There we go. And so look at that. And that is, so I've got some sample outputs. Notice that I do 1 through 5 rather than 0 through n minus 1, because that is the classical way to represent the Josephus problem. So a ring of 5. And again, this is using the toString method that I've already made for you. Okay? Okay, so there you go. And so if you want to test your output, you'd be able to match these. Okay? Now, the other problem is solitaire encryption, or the Pontifex problem. Now, this one's pretty cool if you go out and get yourself a deck of cards to work with, like a deck of playing cards, because you can actually physically work through the process. Okay. Now, this came from somebody else's assignment as well. This was originally made by Lester McCann. I'm a big fan of Neil Stephenson. If you don't know who he is, he's a author who writes a lot. Who writes a lot of stuff, and he has a very huge flaw, which is he doesn't know how to stop writing. So his books are like giant door stoppers. The most accessible of his work is a book called Reamd, which is a misspelling of README, which is about a MMORPG. It's about cryptocurrency. A fictional MMORPG, gold farming, social networking, and criminal methods of the Russian mafia and Islamic terrorists. It's pretty extensive. And he does his research. He does a lot of his research. You'll know more about Russian handguns than you ever thought you'd know about specific models of Russian handguns. You'd also know a lot more about Chinese gold farming, the Chinese gold farming industry, at least at the time that this was written, than you thought you would know. And this is a really good, really accessible one. I think it would be fairly easy to adapt. But the book we're focusing on that he did was written in 1999, called Cryptonomicon, and it is actually fairly math heavy for just reading. It follows 2 stories, one during kind of the 90s, modern day 90s there, and World War II cryptographers. And he talks about basically the basic game, both code breaking and the basic game theory that had to go into. Not basic game theory, but just a basic overview of the game theory that had to go into the idea of decrypting German codes, but also not letting the Germans catch on to the fact that you were decrypting their codes. So it is a pretty cool. So it's a pretty interesting book, and during it, he introduces an algorithm called the Pontifex algorithm. It's called Pontifex to disguise the fact that it uses a deck of cards to do it. This is actually but it's a real algorithm that was created for the book. It includes a description in the appendix. It has like the write-up of it and a Perl script, an awful-looking Perl script. By Bruce Schneier, who is I don't even know if I'm getting his name right, but he's very big in cryptography circles. So basically, he developed it for the book. It's a real algorithm, and the idea is that basically, if you want to decrypt something, encrypt something and decrypt something without in a bit of a method using only a deck of playing cards. The idea here is that you and your compatriot, who you want to communicate with, you basically both memorize a starting layout for the cards. Okay, a starting layout for the deck. You're both going to start out with the deck arranged in the same layout, like this. 1, 4, 7, 10, 13. So here, it's just going up by threes. So 1, 4, 7, 10, 13, 16, 19, 22, 25, 28. So first things to explain here. For the simplified, what we're going to do for this assignment is that we're going to simplify it a bit. So one of the cool coincidences of a deck of cards and the English alphabet is that the English alphabet has 26 symbols in it, and a deck of playing cards minus the jokers and all the, minus the jokers has 52 cards in it, which is twice 26. It's a pretty cool coincidence there. So we can kind of use that to help scramble it. Rather than using a full deck of cards, your assignment here uses half a deck of cards and the 2 jokers, so 28 cards total. Let's say the hearts and the spades, and we leave out the other 2 suits. Okay, aces are labeled as 1s, so basically ace of hearts is 1, 2 of hearts is 2, 3 of hearts is 3, so on and so forth until we get to the king of hearts. The king of hearts, which is 13, and then 14 would be the ace of spades. 15 would be the 2 of spades. So basically, we now have basically given the cards all a label, and now the jokers, we will give them a separate label as well, 27, 28. You can actually tell the jokers apart in most decks. Typically, the most typical ways I've seen is that one is colored and one is black and white. So you just label which one whatever, just so long as you remember which one, and now you are good. So we've got 28 cards, and we memorize a starting position for them. And in our examples, we do this memorization over here, where basically we go up in values by 3s, because that's easy enough for us to remember. We don't have to remember the whole thing. We just have to remember this kind of permutation. So there's, so what we do to encrypt something, okay, is basically we want to take a message and turn it into gibberish. So let's go back to the Romans for a second, okay? All roads lead to Rome, as they say. The history of cryptography starts with Julius Caesar, and not the Caesarean section, but the Caesarean cipher, or the Caesar cipher. It's a very well-known technique, and the idea here is that we have some kind of key that helps us scramble something. Typically, we just simply shift the letters. So here is the English alphabet shifted by 23. Basically, each letter is replaced with 123 letters away. So here we have the quick brown fox jumps over the lazy dog, encrypted into ciphertext. And the idea here is that if you don't know if you don't know what the cipher is, it's gibberish. And this was actually very effective back in the day because, the barbarians, that comes from the Greek word, barbaros, which literally kind of meant the people who just say barbar, because that's what it sounded like if you couldn't speak Greek or later Latin. True story. That's why they're called barbarians. You can look it up. Anyway, so first off, if a barbarian, a non-Roman, captured this, intercepted this, first off, chances are that they may not be able to read in the first place. That's actually probably not a bad guess. Second, even if they could read, this would look like gibberish because cryptography is like why would you need to develop cryptography? So that now, mind you, once this method has spread enough and people knew it, it's like, okay, you only have to check 25 different combinations, 25 different permutations, 25 different keys. So eventually this led way to we need something better. The Veneer cipher was that, and it lasted until like through the end of World War I. Okay. So what you do is you choose some kind of here's the hello world message, by the way, for cryptography, which is attack at dawn. Lemon lemon le. So what is that lemon lemon le? What you do is rather than choosing a single word, you choose a key. Choosing a single key, you choose a key word which has some length, and each letter gets a separate key. So A gets the key L, T gets the key E, T gets the key M, and you basically convert them into numbers, add them, wrap them around, and you get your ciphertext. Okay? And you just repeat it until you need to. So basically you're just adding letters together until, and again, you just simply convert them into numbers to do that. Eventually we give things like, famously the Enigma machine got, in World War II, basically things got so complex we needed stuff to be able to, we needed actual machines to be able to crack these codes. Or ciphers, rather. So now when I say key and we're generating key stream values, what I mean is that we're going to use the deck of cards and we're going to manipulate the deck of cards in such a way that we kind of shuffle everything around a bit in a very deterministic way, meaning that when I do it, you're going to be able to repeat it on your end if you follow the same steps. And each card and every time we do this, we'll reveal a single card, which will then be used as a key for a single letter. So all of these so this is a very slow process to do by hand, but it's fairly effective when you don't have a computer. Okay. So there's 5 steps to generate the key for a single letter. Find Joker A, swap it with the card that's underneath it. So if you go through and you have dum 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 Joker 2 of hearts, it becomes dum 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 2 of hearts Joker. Okay. Find the second Joker, the B Joker, the other one you labeled. Move that one 2 cards down. So if it was Joker 2-3, now it's 2-3 Joker. And again, if it's the last card and it needs to go to the beginning, then it just goes to beginning because it wraps around. This doesn't necessarily have to be done with like a circular linked list, but it's worthwhile to do so. Perform the triple cut. The triple cut's actually where I highly recommend you start, because if you're doing this one, because doing the triple cut will kind of give you the insight you need to doing these problems. Because these kind of problems with we use a linked list rather than an array list, because linked lists are really good at being split up and being swapped, and swapping stuff. Array lists, not so much. It's really hard to split those things up, but you can like split up and rearrange an array, a linked list really easily in O of n time. It's harder in array lists. So triple cut. What you do for that is you take everything above the top Joker, everything below the bottom Joker, doesn't matter which one is which, just top and bottom, and you swap everything above the top Joker to the bottom, and everything that was below the bottom Joker goes to above the top Joker now. I have some examples written on that. Now, how in the world should you code that? A lot of people like to look for things and do their indexes. My advice for this assignment is don't do this like you would like working with a normal list. Instead, consider yourself to be doing the algorithm manually with a table in front of you, nice big table in front of you, and only one hand accessible. How would you do it? Well, with a table and a deck of cards, the most I could do is flip over is move these cards over into separate piles, into basically creating different decks. And then so I'd be adding cards to new decks and removing it from this one, and then removing them and adding them back in. That's how you want to approach this. Basically, think about all the manipulations you'd have to do with it one-handed, and how you would physically do this if you were one-handed. Not clever ways to do it, just how you would do it that would require little thinking on your part. Okay, similar, remove the bottom card from the deck. Look at it. Move that many cards down to the from the top to the bottom. Oh, great. Awesome. Okay, so, nice. Okay, so for instance, say we've got this, so let me go ahead and rig it just slightly. Say we've got this, yeah, it doesn't matter. So suppose we've got this 10 of hearts over here on the for step 4. What we would do is we'd remove it, we'd look at the 10 of hearts and go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Take these cards, move them to the bottom. Okay? And then put the bottom card back. Okay? Last step, look at the top card. Ace of spades, which in our thing would be 26. So keep it at the top, count 26 cards down. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. We've counted 26 cards down. Our top card is the Queen of Hearts. That is going to be our key. All that for one key. But again, your computer can do it faster. But this key would be 12 in our way of doing things. Leave the deck the way it is. And then to generate the next key, we do the same thing. We look for the joker. We move the joker down 1. We move the joker down 2. So let's go ahead, and you do fortunately have the jokers in here. So again, how do you do this? For the triple cut, the way I would do the triple cut is as follows, right? Look at the cards until you get to a joker. And what you're doing is that, actually what to more physically represent it, I'd move the cards into a separate pile. Again, doing this one-handed until we get to a joker, until we get to the joker. I'll leave the joker there. I'll move the joker into the second pile. Until we get to the next joker, which it can take a while if you're doing this one-handed, but again, computer's not. It's not going to be at the end. There it is. So now I found the joker. I'm going to put it there, and then I would simply iterate through all these guys and put them into a separate one. Now, how do I reconstruct this? Well, I have my empty pile right here. You can't see it because it doesn't have any cards in it, but then I take everything from this pile, kind of, right? Because what I'm doing is I'm adding them to the end of a deck. So the order is maintained. Now I take everything here and just add them on one at a time, which would just essentially do that. Then we take everything from here, add it on one at a time, which essentially does that. Take everything from here, from the beginning to the end, and there you go. And there's 52 card pickup. All right, so, and that's how you do that one. Right, so 5 steps there. Now, give me 1 second, because I know you'll want to, like, how do you test this? So you want to be able to just give me the roughly for the input options. I don't really care so much as long as you give me the option to encrypt or decrypt something. That's all I care about. Like, you don't have to actually implement the part that says, oh, see if they want to read it from a file, or whatnot. Because summer session, you've got less time. What I do want you to try to do, here you go, and here you go. So how do you know if you've got something right? And the answer is that there is for this one. For this we have if you use the example key stream over here, where basically you go up with where basically you go up by 3 for every key is up by 3. Next, then here's what then hello will translate into SNISY, and it's snizzy. Okay, it's a gibberish word, but that's what you get. But if you get that, you're going to know it works. Once again, sorry for taking so long to go over these things, but I wanted to make sure you do it. Now, the great thing is that if you decide, you can decide how you want to spend your time, which is that you can try starting the solitaire encryption one or not. Regardless, the starting point is the same for both problems. Implement the circular linked list. Once you're done implementing the circular linked list, all the Josephus has to do is complete main. But on the other hand, if you're doing the solitaire encryption, we've got this separate file I've went ahead and started for you, and you've got to finish that entire other file, unfortunately. But I mean, those 20 extra credit points, getting 220 points out of 20, let me tell you, that can be really nice. I've already done a lot of the hard work for you over here, which is given a letter and a key, give me the encryption, and then I've outlined the code for you. To get the key, so given your deck of cards, to get the key for the next letter, you need to call this function, and then we have 5 separate steps. Step 1, step 2, step 3 to do those. Okay? So once you do those, then you'll be done with main. Now, the only thing I want to really point out here is that you may notice that I'm doing some weirdness over here for encryption, letter and key, and then saying letter minus A. Now, in case you missed this, yes, you can do mathematical operations on chars. Cars are just like they're numerical values. They just get translated into letters. They have a numeric representation in ASCII. This value is I think 97 or something like that. Now, why am I subtracting 97 from every character? Why am I subtracting 97 from every character? The reason I'm subtracting 97 is so that if these are letters, then I want to get them into the range of 0 to 25, because then I can start doing modular arithmetic on them, where A is 0, B is 1, C is 2, C is 3. And if I can do that, then what I can do is I can say, take the value, add the key to it. So if I want to take the letter, so if I have Z and 2, I would get 27, okay, at this point. And then doing modular arithmetic, I would get 1. So it would be 0 would be A, B would be 2. So 2 letters after Z would be B. That's why hence the mod 26. Also worthwhile noting that while in mathematics you could just write value plus key and then the word mod and not need any parentheses. Remember, in programming, this is on the same precedence. Modulo is on the same precedence as times and divide. Hence the parentheses. And then to get it back into the range, we add the A back in. We do the same thing for decrypting, except you notice that instead of key, I do 26 minus the key. That's so that we can, if the key was 3, that moved that letter forward 3 spaces. And rather than trying to move it back 3 spaces, the math is easier if you just move it forward 23 more spaces, right, to do a full rotation of 26. Okay, but this part was already done for you because that part is annoying. And I would have to write it from scratch in class anyway for enough people. All right.